Hello guys, good evening. Welcome to today's class on electricity. Right, so we'll basically revise the most important ideas for your board exam. Right, so we'll revise all the concepts and we will also solve some related problems. So that will be the basic idea of today's class. So before we start off, I'll give you a quick overview of the necessary topics as and when necessary. So first, what is resistance? You know that resistance is right. Supposing what is resistance, you know that resistance is basically equal to rho L upon A. Now, rho is the resistivity of the material. And this resistivity, you know that it is a material property. So, it's a material property, depends on the material. Okay, depends on the material used. For example, copper has copper has a specific value of resistivity. Silver has a specific value of resistivity. Different materials have different values of resistivity. Now, this formula, supposing if you have a cylindrical wire, usually we model our wires to be cylindrical in shape. So, supposing if you have a cylindrical wire of cross section L, sorry, of length L and cross sectional area A, then the resistance of this piece of the wire, supposing let us say this is made up of copper, right? So the resistance of this piece is actually given by rho of copper, which is resistivity of copper into length divided by area of cross section, divided by area of cross section. Okay. So I hope this idea is clear. Let us try to solve one problem. This question I will solve it for you. You can try the upcoming questions. Two wires A and B of same material and same length have radii R1 and R2 respectively. You have got two wires A and B made up of the same material. So if the resistivity is rho, for B also the resistivity is rho, length is also same, but radii. So this is R1 and this is R2. Right. So what is resistance? Resistance of wire A is rho into L upon A. A is nothing but pi R1 square. What is RB? Rho, which is the resistivity, into L divided by area, which is pi R2 square. Right. So RA by RB, if you just calculate RA by RB, this is rho L upon pi R1 square into pi R2 square by rho L. Pi gets cancelled. Rho L gets cancelled. This is R2 square by R1 square. This is R2 square by R1 square, or you can say this is ratio of the resistances. RA by RB is R2 square by R1 square. Okay, so I hope how to apply this formula, the basic idea is clear. I would like all of you to quickly make a note of it and try out a question. Okay. By the way, in today's session, we are going to finish revising electricity in a single shot. I'll try to cover all the important formulae, all important concepts, and some typical numericals. So hopefully by the end of this class, you should be thorough with all the basic concepts in electricity. Right? So quickly make a note of this. Come on. I'll give you a few seconds. All right, let's try question number 2. Question number 2. Look at the second part. What is the resistance of a wire of length L, area A, made up of a material of resistivity rho? You already know that the resistance is rho L upon A. Straightforward answer to part B. But I want you to think about part A and give me the answers. Why is the series arrangement not used for domestic circuits? Think about it and give me an answer. Come on. Tell me some reasons why typically we don't use series arrangement for domestic circuits. Come on. Okay, let's try answering this particular question. All right, let's look at this. Now, supposing you have a few appliances connected in series, right? Let us say this is appliance 1, or let's assume, for simplicity, let's assume that there is a light 1, there is a bulb 2, L2, there is another bulb 3, L3, and so on. Okay. All right. Now, there are multiple issues with connecting them in series. First issue, supposing if one light goes bad, right? That means all the lights also will not glow, because if this light goes bad, this part of the circuit becomes like an open circuit. So current does not flow to the other circuits L2 and L3. Right? This is number one. Number two, in your residence, supposing for example, we will not have only three lights. We'll have multiple lights, fans, air conditioners. You will have geysers, you'll have refrigerators, etc. So you keep connecting everything in series to a 220-volt main. Now what will happen? The more and more electrical component that you connect in series, what is going to happen? You know that the equivalent resistance in series is R1 plus R2 plus R3 plus so on. So supposing if you connect 10 different appliances, your R equivalent is going to be really high. That means your current is going to be P by R, which is 220 divided by R equivalent. But we know that this R equivalent is really big, right? Therefore, the current will be small. So what happens when when you connect so many different appliances in series, the current actually drops, and sometimes the current might drop to a level that it's not sufficient enough for that particular electrical component. Number two. So there is one issue with current also, right? The first idea is supposing if one appliance goes bad, current will not flow to the other appliances as well. Number two, the more and more appliances you connect, the more is your R equivalent. More is your R equivalent means lesser is your current. Lesser current might not be useful to sort of run that particular electrical equipment. And number three, so if you look at modern day equipments, right? For example, something like air conditioners, refrigerators, etc., they are designed to operate at a certain voltage. Right? For example, your refrigerator, it might be designed to operate at 220 volt, which is the standard main supply that you receive. Right? But in a series combination, each electrical component is exposed to a different potential drop. Right? For example, if this is 220, maybe here you will have 110, maybe here you will have 100, here you will have 10 volt. I'm just giving you an example. If you add all of this, you get 220. So each electrical component is exposed to a different potential drop. Right? Each electrical component is exposed to a different potential drop. And number four, controlling each of these electrical equipments independently, that's also a problem. Supposing if you want only L1 to grow, you want to turn off L2, once again a problem. Right? So these are some of the reasons why we don't prefer series arrangements in domestic circuits. Right? I hope the basic idea is clear. Good. Let's try question number three. Question number three is a very good question. I see a lot of children making mistakes in such kind of questions. So I'm letting you know upfront. So try and solve this particular question. Come on, try question number three. 1 more minute to go. All right, let's try solving this particular question now. Okay, first one common mistake that a lot of children make so that you don't make it in the exam. Now, what is given? A wire of resistance 10. 10 means what? Wire of resistance 10. So this is basically 10 ohm is drawn out so that its length increases to 3 times its original length. Calculate its new resistance. So there is a wire. Let us say length L, area of cross section A, resistivity rho. Its resistance is basically 10 ohms. That means rho L upon A, that is basically 10 ohms. Now you're stretching this wire. Drawn out means what? You're pulling this wire, you're stretching that wire such that the length becomes 3 times its original length. Right? So the length has now become 3 times original length. Okay, calculate the new resistance. Now, one common mistake that a lot of children make is the following. Is to assume resistance is equal to rho L upon A. Right? Rho is rho. L, instead of L, you have got 3L divided by area. So 3 into rho L upon A. Rho L upon A, you already know, is basically 10. So this is 3 into 10, that must be equal to 30 ohms. Right? I see many children solving the problem like this. But this answer is actually incorrect. Why incorrect? Why is this incorrect? Because you are assuming that when the length becomes 3L, the area remains A. That is the mistake. This when length becomes 3L, area does not remain the same. Area also changes. So this answer 30 is incorrect. Right? So first you should figure out what is this area. First you should figure out what is this area. So for example, here I'll make it as L0. I'll make it as L0 A0. Here also, let us say this is 3L0, L0 A0. Right? Otherwise, it will be confusing. R is equal to rho L upon A. Here also, you suddenly have rho into 3L by A. Right? So, formula, I will use R is equal to rho L upon A. The initial values, I will use it as L0 and A0. Now, how do you solve the problem? See, first thing, when you're taking a wire and you're stretching it, the volume of the wire remains conserved. Right? You're not going to change the volume. So, therefore, let us try and use that idea here. Area of cross section is A0 into length is L0. So area into length gives you volume. That must be equal to area into length gives me volume. That must be equal to the new area is A dash. A dash into 3L0. A dash into 3L. Right? Now what do you have here? Let's figure out what is A dash. A0 remains A0. L0 cancels. So you end up having A dash must be equal to A0 by 3. So that means A dash must be equal to A0 by 3. So when length becomes 3L0, area becomes A0 by 3. Okay. So therefore now you can calculate resistance is equal to rho L upon A. Rho I will written it as rho. L is nothing but 3L0 divided by A is nothing but A0 by 3. So this is 9 into rho L0 by A. This is 9 into 10. That must be 90 ohms. So therefore, the right answer to this question is 90 ohms. Please make a note of it and ensure that you don't make this mistake in the exam. Is this question clear? Shall we move on further? Tina, is this clear? I'm assuming that this question is clear. Let's quickly move on further. Try question number 4. Come on. Try question number 4. By the way, this is a revision session. So if you've got any doubts, please post it in the chat box. I'm looking at your chat box. Any doubts, I'll get it clarified. By the way, Sai Ram, see for this question, it is given that 3 resistors, 2, 4 and 6 are connected in series. Find the equivalent resistance. If a potential difference of 12 volt is applied, find the current flowing through the circuit. Now, if they just give you this and not the circuit diagram, you must be able to draw the circuit diagram. Right? So first, let's draw the circuit diagram. What is the idea? 3 resistors. So you've got a 2 ohm, 4 ohm and 6 ohm. They are connected in series. Right? Find the equivalent resistors. And the other thing is they've asked, supposing if you have 12 volt applied, what must be the current flowing through the circuit? Now from the given data, there is no way you could draw a different circuit because from the given information, 2, 4 and 6, they're all connected in series. 12 volt is connected like this. Find the current flowing through the circuit. How will you figure out the equivalent resistance? Supposing in series, if you want to figure out R equivalent, you know that it is nothing but R1 plus R2 plus R. In parallel, 1 by R equivalent must be equal to 1 by R1 plus 1 by R2 plus 1 by R. 1 by R equivalent is nothing but 1 by R1 plus 1 by R2 plus 1 by R. Now, how do we figure out the equivalent resistance here? R equivalent must be equal to 2 plus 4 plus 6, which is 12 ohm. Right? So that means you could redraw the circuit to a circuit that looks like the following. This is 12 volt. Instead of 2, 4 and 6, you can replace all the 3 resistors with one single resistor which does the same job. But the resistance must be 12 ohm. Now what must be the current? You know that current must be equal to V by R. So this is 12 volt divided by 12 ohm. This is 1 ampere. So the right answer to this question is equivalent resistance is 12 ohm and this is 1 ampere. Alright. Sriram, is this question clear to you? I'm sorry, Sairam. Let me know if this is fine. We'll move on to the next question. Children, please confirm if it's clear so far. Any doubts, get it clarified then and there. If it's all clear, do let me know that it's clear in the chat. Okay, then we'll proceed on further. I'll give you a few seconds, absorb these ideas. If everything is clear, quickly let me know that it's clear. We'll move on further. All right. All right, let's move on further. Let's try question number 5. Now, what is given? A circuit diagram showing a battery of 4 cells, a plug key, a 6 ohm resistor, an ammeter, and a voltmeter across the resistor. By the way, remember all of these are your previous year board exam questions. Now, when a question like this is asked, now they're not simply trying to check whether you know the circuit symbols for all of this. They're also trying to figure out if you know how to connect an ammeter and how to connect a voltmeter. Now, remember, ammeter measures current and voltmeter measures potential drops, or in the language of the textbook, potential difference. Okay, so now what do we have? Draw a circuit diagram showing a battery of 4 cells. So let us say 1, 2, 3 and 4, a plug key and a 6 ohm resistor. Remember, whenever you are connecting an ammeter, you should connect it in series. So the logic is, supposing you have an ammeter here. So whatever current enters through the 6 ohm resistor, the same current exits the 6 ohm resistor, the same current enters through the ammeter. So in series, same current passes through all the electrical components. Therefore, since an ammeter is trying to measure current, ensure that you are connecting it in series with the resistor. Right? And how do you connect the voltmeter? Connect the voltmeter across the resistor, because it must measure the potential drop across the terminals of the resistor. So this is the voltmeter. Right? So ammeter is connected here, voltmeter is basically connected here. I hope the idea is fine. All right. Let's try another question. It's a good one. I'll give you 3 to 4 minutes. Try question number 6 from your worksheet. Come on. Time is 6:30. We will discuss this at 6:30. Take 4 minutes. Draw the diagram. Then solve this bit by bit. All right. All right, let's try this question. What do we have here? An electric lamp of resistance 20 ohm and a conductor of resistance 4 ohm are connected in series to a 6-volt battery. So first let's draw the circuit. So we have got an electrical lamp of resistance 20 ohm and we have got a conductor of resistance 4 ohm. They are connected in series to a 6-volt battery. Okay. We have been asked to calculate the total resistance of the circuit. So how will you calculate? So the idea is simple. R equivalent. These two resistors are in series. So R1 plus R, which is nothing but 20 ohm plus 4 ohm. That must be equal to 24 ohms. That must be equal to 24 ohms. That means you can redraw the circuit to look like the following. You can say the circuit is identical to this circuit where you have replaced both of these resistors, which is a 20 ohm resistor and a 4 ohm resistor, with a single 24 ohm resistor. With a single 24 ohm resistor. Right? With a single 24 ohm resistor. Now, when you do this, this is 6 volt. How can you figure out the current? You know that current is nothing but V by R. So this is 6 divided by 24. This is 1 by 4, which is 0.25. So therefore, the current flowing through the circuit is 0.25 ampere. The total resistance is 24 ohms. Now, third question, the potential difference across the lamp and across the conductor separately. Right? So you know that this 1 by 4 ampere is flowing like this. So for this bulb, if you look at the potential drop along the direction of current, you know it is nothing but IR. So I is 1 by 4 into R. What is the value of R? 20. So this is nothing but 5. Okay. And this one, the potential drop along the direction of current, once again is IR. I is nothing but 1 by 4. R is nothing but 4. Effectively, this is 1 volt. So this is 5 volt and this is 1 volt. 5 volt plus 1 volt put together is nothing but 6 volt. That is a potential drop of this particular. That's the EMF of this particular battery. Right? So the potential difference across the lamp is actually 5 volt. Across the conductor is 1 volt. But when you add them together, this 5 volt plus 1 volt, you end up getting the 6 volt. Alright. So what is the power consumed by the lamp? So once again, a frequently asked question. So power, there are three formulae for power. One, you can use IV, or you can say power must be equal to I square R, or you can say power must be equal to V square by R. Supposing if I and V are given, use power is equal to IV. Supposing if I and R are given, use power is equal to I square R. Supposing if V and R are given, use power is equal to V square by R. Now, supposing if you want to figure out energy. Now, energy is simply power into time. Right? Because power is nothing but rate at which energy is being spent or energy is being consumed. So that's the idea. So energy is nothing but power into time. So this is IVT. Energy is I square RT and energy is V square by R into T. So you've got three formulae for power and three formulae for energy. So all of this is for power. All of this is for energy. This is for power. This is for energy. Right? Now power consumed by the lamp. So power consumed by the lamp. So power, I'm going to use I into V. I is 1 by 4. V is the potential drop across the lamp. That is nothing but 5. So this is 5 by 4. How much is this? This is 1.2. 5 by 4 is nothing but 1. And remember, the unit is nothing but watt. Right? So the unit of power is nothing but watt. Unit of energy is nothing but joule. Make a note of this one also. Energy is measured in joule. Power is measured in watt. Okay. I'll pause here for a few seconds. Please make a note of it. Come on. Sairam, is this clear? Tina, Sairam, is this clear? Take a minute and let me know. Children, please let me know if it's clear. If it's not clear, please ask. Please mention that it's not clear. We'll go over it once more. For your board exams, I don't want you to go back and sort of revise this chapter once more. Most of the concepts I would like to cover it here. A quick go through should actually help. Any doubts that you've got, get it clarified. All right. So I'll give you a few seconds, make a note of it. If you're done with this question, you can try question number 7. All right, I'm assuming that this question is clear. Let's try out another problem. Try question number 7. Saket, come on, try this out. All right, let's try to solve this particular question. Now, what is given? An electric iron consumes energy at 880 watt when heating is at maximum and 440 watt when heating is low. If source voltage is 220 volt, find the current and resistance in each case. Now, I think Sairam has asked, sir, question, if source is not understand, sir, 220 volts. So I think you're trying to say you do not understand what it means when somebody is saying source voltage is 220, right? So, see, if you remember how does your iron box work, so if you look at your iron box, right, you've got those settings. I'll show you this picture. Hold on. Let me show you a picture. Please hold on for a second. Let's say you have an iron box. All right. See, you might have noticed that here you have got this turn knob, right? By turning this knob, you are able to adjust the heat settings. For example, cotton, linen, etc. You would iron it at high power, right? You want the heat to be really, you want a lot of heat. And for delicate things like, for example, in silk, or sometimes if you're ironing some synthetic clothes, etc., we keep the heat level really low. Now, what is happening? By the way, all you're doing this when this is connected to the socket. Now, what do you mean by source voltage is 220 volt? For example, when you're connecting this to the socket, that means you don't have a battery there, but you have the EMF which is equivalent to 220 volt, right? So when you connect something to a socket, the usual line voltage that we get is about 220 volt. In India, it's about 220 volt, right? So the iron box throughout is connected like this, right? But when you're changing the setting, depending on what you keep, now what is going to happen? The resistance is going to change within, and therefore the energy that it consumes is also going to change. Now, the idea is an electric iron consumes 880 watt when heating is maximum and 440 watt when heating is low. You know that power is nothing but IV, right? When heating is at its maximum, the energy is, when the heating is at its maximum, the power is 880. 880, that must be equal to I into 220. Right? From here, what do you end up getting? I must be equal to 880 divided by 2. So this is nothing but 4. So when the iron is actually heating at its maximum, the current is 4 amperes. Once you know the current, you also know one more formula for power. Power is I square R. Right? So this is 880. That must be equal to I square is 4 square 16 into R. 880 divided by 16. That must be equal to R. Now, how much is this? 880 divided by 16. Let us check. This is, I can say 18 is 8. This is 110. This is 2. So R must be equal to 55 ohms. So when the setting is at maximum, right? When heating is at maximum, the current is 4 amperes and the resistance is 55 ohms. Now, similarly, the same calculation you do when the heating is minimum. Once again, you know power is equal to IV. So this time the power is only 440. Must be equal to I into 220. I must be equal to 440 divided by 220. So this is 2 times. So therefore you end up getting I is equal to 2. Now once you figure out that I is equal to 2, you also know that power is equal to I square R. So this is 440 must be equal to 2 square is 4 into R. Right? So 440 by 4, R must be equal to 110. R must be equal to 110 ohms. Make a note of this, come on. This would be the right answer to this question. I hope this is clear. Sairam, is this idea clear? Make a note. I'll give you a minute. Make a note of it. If you are done with this, you can write question number 8. Okay, let's move on. Quickly try this next question. Come on, question number 8. Very good, Saket. Sairam, is your doubt also clear? Try question number 8. Come on. All right, let's try out this question. Now, what do we have? Two lamps rated 100 watt at 220 volt and 60 watt at 220 volt are connected in parallel to a 220 volt supply. Find the current drawn from the supply. So you have a 220 volt supply, right? And there is one lamp. The power rating is 100 watt at 220 volt. What do you mean by 100 watt at 220 volt? Supposing if you take that bulb and connect it to a power source, right, which is offering a potential drop of 220 volt, the lamp would actually consume energy at a rate of 100 watt, right? 100 joule per second. Every second, 100 joule it will consume. So now one more this thing. This is 60 watt at 220 volt. This is 220. Now, how do you figure out the current? Current drawn from the supply. So let us say this current is I. You know that this current, when it goes to this junction, it splits into I1 and I2. So you know that I must be equal to I1 plus I2. But from the formula of power, you know that power is nothing but IB, right? When power is 60, the current is I2 and V is nothing but 220. So 60 divided by 220 is I2. Similarly, for I1, what do I write? 100 must be equal to I1 into 220. 100 by 220 must be equal to I1. So what is I1 plus I2? I must be equal to I1 100 by 220 plus I2 60 by 220. So this is 160 divided by 220. I must be equal to 160 divided by 220. So how much is this? This is 8 2s are, this is 11. So 8 by 11. I must be equal to 8 by 11. That is the current drawn from the supply. However, remember when you're writing it in the exam, so you cannot leave it like this in fractions. So you might actually convert it into decimals and then you need to give the value. Right? So what is 8 by 11? So 8 by 11 is roughly 0.7272 and so on. So you should convert it into decimals and simplify the answer and give along with the units. Along with the units. I hope the idea is clear. By the way, a couple of small tips for writing your board exam. Now make it a point to check your paper after you write your finish your paper. Number 2, when you're checking, make a checklist mentally, right? And ensure that you have written down the units for every answer. So after you simplify and write down the answer and box it, ensure that your answer has units. Suppose if current is asked, if you write 0.7272 without mentioning ampere, now I could interpret it to be a milliampere. I could think it's microampere. I could think it's mega ampere. Who knows what ampere it is, right? So mention it along with the unit, number one, and ensure that you draw your circuit diagram wherever necessary, right? So take care of these small things while you're writing the board exam. All right. Units, very, very important. Sometimes if you need to convert units, ensure that you also convert units. All right, let's try one last question and wind up. I would like all of you to try question number 10 from your worksheet. It's about commercial unit of energy. Try question number 10. State Joule's law of heating, you already know. Just do the problem part. An electric refrigerator rated 400 watts, run 8 hours per day. What is the cost of energy to run it for 30 days at rupees 3 per kilowatt hour? Try this out. All right, let's try to solve this question. What do we have? An electric refrigerator rated 400 watt, runs 8 hours per day, right? So first, let's figure out how much energy it consumes. Energy is nothing but power into time. Power is 400 watt into time is 8 hours. This is per day, right? And I'm running it for 30 days into 30, right? So this is 4 into 8 into 3 into 1000 watt hour, right? So 4 8s are 32. 32 into 3. This is 6. This is 9. So this is 96. This is 96 into 1000 watt hour. 1000 watt hour is nothing but 1 kilowatt hour. 96 kilowatt hour. So the energy is nothing but 96 kilowatt hour. By the way, sometimes in an MCQ, they could ask you what is kilowatt hour. They could ask you whether kilowatt hour is a unit for energy or power. Just because you see watt here, immediately do not mark it as a unit for power. It is actually unit for energy. This is watt hour, right? Watt hour. So this is power into time. So that gives you energy. Kilowatt hour is a unit for energy and not power. It's a unit for energy and not power. It's a unit for energy and not power. It's a unit for energy and not power. All right. Okay. Now you know that 96 kilowatt hour, that is basically the energy that it consumes. And you are actually running it for 30 days at rupees 3 per kilowatt hour. So for 96 kilowatt hour, 96 into 3, this is 18, this is 28, this is 280. So you're going to spend 288 rupees. By the way, one common tweak that they can do to this question in the board exam is they could say, calculate the cost of energy to run it for one whole month in the month of June. Or they could say, calculate the cost of energy to run it for one whole month in the month of July. Now remember, June, July, few months have 30 days, few months have 31 days. So it depends, right? So that is why which month, whether it has 30 days or 31 days, that is also important. Sometimes, supposing if they give you a particular month which has 31 days and you estimate only 30 days, that's going to give you a wrong answer. It has nothing to do with physics, but this is a way in which sometimes you also tweak the question. Okay, so I hope this idea is also clear. So let me stop today's lecture here. So I've tried my best to cover some of the important concepts for your board exams. Right, I've also pointed out some key mistakes that you could be making. I hope all of you found this session useful and interesting. Please go back and finish your revision for this particular topic today itself, because the ideas will be fresh. Quickly go through and finish your preparation. Right, or at least in the next 1 or 2 days, because you've attended the session, it should be easier for you to quickly go through the ideas, because the session would have helped you recollect some of the ideas. So quickly finish the revision and move on to the next chapter. Once again, wishing you guys all the very best for the board exam. Looking forward to meeting you all in yet another interesting session sometime soon. Till then, take care. Bye-bye.